Today we are going to discuss energy. We'll see what are the different types of energy. Of course, we'll focus more on mechanical energy. We'll take potential energy and then kinetic energy. We'll try to find out the expression for potential energy of a body which is kept at certain height. Then the potential energy is stored in a stretched spring. We'll then derive the expression for kinetic energy. Then we'll discuss law of conservation of energy, and we'll see some applications of that, especially in the numericals. All these we'll discuss in today's discussion. It is the capacity to do work. So energy is the capacity to do work. That means the body which has more energy, definitely it can do more work. The one which has less energy, it will be able to do less work. Why we are saying that? Because whatever is the work done by a system, that work done by a system is stored as the energy in the other system on which the work is being done. So the system which is doing work will be losing its energy. So obviously, if a particular system has more energy, it means it can do more work. So this is how we define energy there. Now we have the energy in the different forms there. We have the mechanical energy, we have gravitational energy, we have magnetic energy, we have electrostatic energy, nuclear energy. All these are different types of energy. Even the geothermal energy you can take, wind energy we have. So these are all different types of energy. Here we'll concentrate more for the mechanical energy. And in mechanical energy, we have two types of energy. One is the potential energy and other is the kinetic energy. Now, when we take potential energy, it is the energy stored in a body whenever there is a change in its shape, size or position. So basically you can say that it is the energy possessed by a body due to a change in its shape, size or position. So potential energy, if you consider, energy, it is the energy possessed by a body due to a change in its shape, size or position. Like you have suppose a body and we are changing its position. Like you have a body kept at particular position, we are lifting it to certain height. So we are changing its position. So in that case, definitely there will be some work done in changing its position. Whatever work is being done by that external agent, it will be stored as its potential energy. Similarly, if suppose you have a wire or you have a rod, you are stretching that one. So if you are changing its shape, in that case, there will be energy stored in it, because in changing its shape or size, you are doing work. And whatever work is done, it will be stored as its potential energy. You have a ball and you are compressing the ball. So that means you are deforming it. Or you are changing its size. So again, there will be the work done, and in that case, there will be energy stored in the body. So we'll see what are the different types of the potential energy. We'll just discuss what are the different types of the potential energy stored in the body. Of course, here in this particular topic, we'll concentrate more for the change in the position there. And of course, one or two example we'll take where there is a change in the shape or size. Like you have a spring, you are stretching the spring, you are compressing the spring, then you are doing work. And whatever work is being done, it will be stored as its potential energy. So we'll try to derive expression for those potential energy of the system there. And in potential energy, do remember one thing. There is nothing like absolute value of the potential energy. Like when we take a body and we say that what is the potential energy? So it is not basically the potential energy in absolute sense. It is basically the change in potential energy. Because there is no reference frame what we can take where the energy can be taken to be zero. We can take reference where we can assume that if the measurement is done from there, the energy may be taken zero, but it is not basically the absolute one. So obviously, whenever we talk about the potential energy will always be expressed there in the form of the change in potential energy. Like if a body is lifted from one point to another, we are lifting the body from this position to this one. So here, if you want to find what is the potential energy, so basically it is the change in potential energy. Whatever the potential energy was here and the potential energy which it has possessed at this point, the difference of the two we express there as the potential energy. So it is basically the difference in potential energy. Here, if you take this reference there, that here the energy level is zero, in that case, whatever it will be the difference, that will be the potential energy of this particular position. But in fact, it will always be the change in potential energy. Another term is there, that is the kinetic energy. Kinetic energy is the energy possessed by a body due to its motion. So if you consider kinetic energy, which is also another type of your mechanical energy. So it is the energy possessed by a body due to its motion. And how do we measure that? We basically try to find out what is the work done on that body when its speed is changed. Like from the rest, we are bringing it to a particular speed. So whatever is the work done, that will be gained as the kinetic energy of the body. Or if the body is moving there with certain velocity, whatever is the work done to bring it to the state of rest, that will be the measure of the kinetic energy. So let's start first with the potential energy. Suppose we want to find potential energy of a body kept at certain height. Like here, suppose you have a body of mass m and this body is kept at a height h from one particular reference level. That means we are assuming that initially the body was here and we have lifted the body up to this particular position where the height becomes h. So we want to find what is the potential energy there. For this, we'll find out what is the work done in lifting this body. Whatever will be the work done in lifting the body, it will be stored as the potential energy of the body. So here, if we have the body of mass m, its weight will be acting downward, that is mg. So in order to lift the body, we need to apply a force F, and this F should be equal to mg. That will give the minimum amount of force which is required to lift this one. And then with this force, we are moving it to the point which is at a height h. So the force required to lift the body will be equals to mg. Now here, some may be confused that if the force which is applied is same as the weight, how the body will move, because they will be cancelling one another there, or net force is zero. Net force is zero is simply indicating that there is no acceleration in the body. That means no change in the velocity. So with little jerk or anything, if you just move the body with this particular force which is equal to mg, it will continue with that particular state or that particular velocity. We are taking the minimum velocity so that you can find out whatever is the work done in lifting that, it is directly getting converted to the potential energy and the body is not possessing any kinetic energy at that point. So here, now if we lift it through height h, so work done in lifting through h, that will be F into h. And what will be this work done? This is your mg into h, or it is your mgh. So work done is your mgh. And how we have defined potential energy? Here we have taken that whatever is the work done on the system, it will be stored as its potential energy, if you assume that there is no other form in which the energy gets converted. So in this case, as the work done is your mgh, so the potential energy stored will be equals to mgh. Again, do remember what we are taking this potential energy, we are assuming that this level has the value of potential energy 0, or you can simply say in that case it will be mgh, whatever is there potential energy, or at this particular point with respect to this, the difference of the potential energy or the change in potential energy will be equal to mgh. Do remember one thing, it is not the absolute value of the potential energy here, it is basically the change in potential energy. Because had the body been at some other point, or our reference should have been somewhere else, like if it is here, in that case this reference level is suppose at a height h1 and this one is h2. So in this case, what will be the difference of the potential energy? In that case, you'll have to again consider that it will be your h2 minus h1 for this particular level, because here with respect to this it will be your mgh1, here it will be mgh2. So if you take the difference, it will give you the potential energy as mgh2 minus h1, or that is your mgh. So basically it will be the difference of the potential energy. So this is how you can get the potential energy of the body at a height h, or difference of the potential energy. Let's now take potential energy is stored in a stretched spring. We are taking an ideal spring, we are stretching it, we want to find how much is the potential energy is stored in it. So for this, again we'll try with the same way. That means we'll try to find out what is the work done in stretching it. So here again, if this is the spring of a spring constant K, if there is a force F applied which is producing an extension X there. F is the force which produces an extension X. So this F will be equals to Kx. Now, if I stretch it further through dx, so the small work done in stretching it through dx, this will be equals to how much? It will be your f dx. Now, if I put for f, this is your kx dx. So this is your small work done. If you want to find total work done when its energy length changes by small l, so total work done in stretching it through l, that means it is your kx dx integral from 0 to l, and this will be equals to how much? It is k x dx integral is how much? X square by 2, limit is from 0 to l. So this is equals to k by 2 and this is l square minus 0. So this is your half k l square. So as the work done is half KL square, as we have already said, whatever will be the work done on the system, it will be stored as the potential energy there on which this work is being done. Therefore, potential energy is stored this is your half K L square. Remember, for finding potential energy, as we require to do find out the work done. So if you know how to find the work done in lifting the body, in stretching a spring, or what is that expression, you can use that one and simply substitute it here when you know that work done on the system will be stored as its potential energy. So this will be equals to your half K L square. Let's now take kinetic energy. Kinetic energy, we have defined that it is the energy possessed by a body due to its motion. And we measure kinetic energy by the work done in changing its velocity from 0 to a particular value, or the work done in bringing the body moving with certain velocity to the state of rest. We measure in that way. So let's try to find out expression for kinetic energy, derive the expression for kinetic energy. So suppose we have a body on which F force is acting. Body has the mass m. So in that case, this F will be given as your m dv by dt, or F is equals to ma you basically take. And A we can write dv by dt. Remember, of course, we are assuming that the mass of the body is not changing. So that is why we can use the expression F equals to m dv by dt. Otherwise, if mass is changing, then the expression will be different, because there F expression, it is basically rate of change of momentum. So it is your mv, which we write it as m dv by dt plus v dm by dt. So this is basically the expression for force on the body. But if you consider the mass constant, for this term there, dm by dt will be 0. So dm by dt is 0 by dt. This is 0 for constant mass. And in that case, this F will be simply m dv by dt. So that will be the expression that we have used here. Now let's assume that with this force, the body moves through a distance ds. So here, this ds is the distance through which it is moved, and at that particular moment the body has the velocity v. So you know that v is your ds by dt. So what we can get from this one, ds will be your v dt. Therefore, a small work done in the displacement ds, the force will be your F, and this multiplied by ds, that is your dw, that is the small work done. And if you substitute it here, m dv by dt into, for ds we are putting v dt. This dt you can assume it is cancelled, and now we have mv dv. We basically want to get rid of the term of time there, so that we can find what is the change in its velocity only. So here, this is the work done. Therefore, total work done when the velocity changes from 0 to v. So in that case, it is your m v dv, 0 to v, m v dv is your v square by 2, 0 to v, and that will be equals to m by 2 v square minus 0, or that is your half mv square. Now we have defined that whatever is the work done in changing the velocity of the body from 0 to a particular value is the measure of the kinetic energy. Therefore, the kinetic energy will be equals to half mv square. So this is the expression for the kinetic energy. Remember, we can use this one also to derive your work and the energy theorem, where we take that whatever is the net work done on a system by all forces, that is equal to the change in kinetic energy. So there, this is suppose the work done and you are changing the velocity, suppose v1 to v2. So in that case, that expression will be your mv2 whole square by 2 minus v1 whole square by 2. That means it will be your kinetic energy in the final state minus kinetic energy in the initial state. That means difference of the kinetic energy. But here let's just take that the kinetic energy we are getting as your half mv square. Some important relation also we can get for kinetic energy in terms of the momentum and other. And those expressions are very useful because many times many conceptual type questions or many numericals are there based on that relation. So let's take the relation between kinetic energy and linear momentum. So it is the relation between kinetic energy and momentum. Now, kinetic energy we have taken as your half mv square. This is the kinetic energy. If you simply multiply by m and divide also by m, so the term in the numerator will be your mv whole square divided by 2m here. And what is this term? This is the momentum. So this is your p square by 2m. This is the kinetic energy. So this is the relation between kinetic energy and momentum there. You'll get many conceptual type questions or short answer type question, numericals based on this. Like it may be said there that two bodies are there which are having same momentum, but their masses are different. Say it is given that m1 is greater than m2. Which one will have more kinetic energy? So now you can see for same p, that is the linear momentum, kinetic energy will be inversely proportional to mass. So in that case, the body which has a smaller mass will definitely have more kinetic energy. So the body, that means the kinetic energy of 2 will be more than kinetic energy of 1 or m1. Or it may be said that for two bodies, if their kinetic energies are same, how the momentum will be related. Like if suppose the two bodies have their masses in the ratio 1:4. What is the ratio of their linear momentum if they are possessing the same kinetic energy? So for same kinetic energy, if it is same kinetic energy, then p square will be proportional to m, because this is constant. P square will be proportional to m, or p will be proportional to root over m. So if the masses are in the ratio 1:4, so in that case p1 is to p2 will have the ratio 1:2. So this type of some conceptual type questions you can get, where you can use this expression and give the correct answer. Few more numericals are there where it says that if the momentum of a body increases by 10%, what is the percentage change in kinetic energy? So you take this, suppose initial momentum is p, the new momentum will be how much? It will be 10% more. So in that case, it will be your p plus 10% of this. That means it is your 0.1 p. So basically it will become how much? 110%. So this you will get as 1.1 p there. So p square will be your 1.1 whole square. If you want to find percentage change, find what is the percentage change in the kinetic energy. That means it will be your p2 square minus p1 square by 2m there. So in that case, you will get it as your 0.21 multiplied by 100, that is 21%. That will be the percentage change in the kinetic energy when the momentum increases by 10%. If the momentum increases by 20%, the nu will be how much? It will be 1.2 times the original one. So if you take a square, it is your 1.44. So in that case, momentum will increase by a percent, that is 44% there. So that way you can do. Next is your law of conservation of energy. You all know that total energy of an isolated system is always constant. Total energy of an isolated system, that will be constant. Or another, which is the most common statement of the law of conservation of energy, is the energy can neither be created nor be destroyed. It can only be transformed from one form to another. That is the most traditional statement of the law of conservation of energy. But here, if you consider the total energy of an isolated system, definitely you will look out for all the different forms of the energy which may be present there. And you can see that what are their changes. And if you find out what was the total energy before and after some time, or after some particular incidents there, if you want to find the total energy, you will always find, if it is an isolated system, in that case it will always remain same. So that is how you can use that one for the different cases there. Why we are not taking that total energy energy conservation statement as the energy can neither be created nor be destroyed? Because if you are using that one, in that case you are not allowing the conversion of the energy through the different form. We have the mass energy conversion also, but of course there normally it does not happen in the day-to-day life there, or under the normal situation or the cases which we take. That is why the mass term will remain same there, energy value will remain same. So we say that energy will be always conserved there. But in fact, if you take for a general case, it will be the mass energy that will remain constant. So what we talk as the total energy of an isolated system, we are not allowing it any other form there where it is getting converted, or to other system it is getting exchanged. So there you can simply apply. One very common method, or you can say example, where we can show that law of conservation of energy is obeyed when a body is in free fall. You consider that you have a body, suppose of mass m, at a particular height, which is suppose capital H, and here its velocity is 0. This one, suppose this position I take it as A, and after that it suppose falls through height small h, and there when it falls through that, once it reaches this point, suppose I call it as the point B, this is your basically H, and this is the point B where the velocity becomes suppose V, and after that once it strikes ground or the reference level, which is suppose the point C, here the velocity is capital V. So if you consider the total energy at A, it will be potential energy at A plus kinetic energy at A. Potential energy at A will be how much? It will be your mgh, because it is at a height h, and kinetic energy will be 0 because its velocity is 0 here. If you now consider the total energy at B, this is potential energy at B plus kinetic energy at B. Now potential energy at B will be mg. What is its height? This was your h, this was your capital H. So that means this level or this height will be your capital H minus small h. So potential energy will be mg capital H minus a small h plus the kinetic energy at B. Now if the velocity is v, here it was 0, so how much it will gain velocity? V square will be 0, that is u square plus 2gh we are using, 2gh. So this is your v square. So kinetic energy, that is half mv square, will be your half m into 2gh, and that is equals to mgh. That means the total energy at B, we can take it as your mg capital H minus a small h plus mg small h, which is your capital mgh. This will get cancelled. Similarly, if you take the total energy at C, this is your total potential energy at C plus kinetic energy at C. Potential energy will be 0 now because it is striking this particular reference level. And here we have the kinetic energy at C. If I take the velocity as v, so it is v square will be 0 plus 2g capital H, and that will give the kinetic energy at C as half m into 2g capital H, or that is your mg capital H. That means here if I substitute, it will be how much? mg capital H. Now you see total energy at A, this is your mgh. Total energy at B, that is also mgh. Total energy at C, this is also mgh. So what we get? Total energy at A, same as total energy B, same as total energy at C. So we can show that law of conservation of energy is obeyed in case of body in free fall. We are assuming there is no other form in which the energy is being lost. We are just taking the conversion from potential to kinetic there. There may be air resistance. So if air resistance is there, in that case there will be some work done against that air resistance. So you'll have to find what is the work done there. And there also, if you apply law of conservation of energy, you will find that total energy at any point, if you consider all the different forms in which the energies have been transferred there or it is possessed there, it will always be constant. Let's now discuss work energy theorem. So work energy theorem. Now the statement of the work energy theorem is the total work done or net work done by all the forces on a body is equal to change in kinetic energy. Net work done by all the forces is equals to change in kinetic energy. So net work done by all the forces is equal to change in kinetic energy. Now, if you have to derive this one, in that case, net work done we are taking as the change in kinetic energy. So delta W is your change in kinetic energy. This is what we are doing. So here again, if you consider, we have already taken, suppose the work done, this was your integral dW and this was your f ds integral. F we have taken as your m dv by dt, and here it was your v dt for ds, and this we have to integrate. This will be equals to your mv dv integral. Now if I am assuming that the velocity is changing from v1 to v2, this will be your m v2 square by 2, limit will be v1 to v2. That can be written as your half m v2 square minus half m v1 square. And what is this one? This is the kinetic energy in the second position. This is the kinetic energy in the first position. That means this is basically your change in kinetic energy. And this is your work done. So this is basically your work energy theorem. Whatever is the total work done by all the forces. When we say all the forces, that means you take the different forces acting on the system there. All the different forces. So if you consider that, definitely you will get that the total work done will be equal to only the change in kinetic energy. You can get many numericals based on that and you can solve it there. Now here, just try to understand one thing. We say that whatever is the total work done by all the forces is equals to only change in kinetic energy. But what about the potential energy? Potential energy is also there. So if there is a change in the potential energy, how will say that it is only the change in kinetic energy? The answer to this one is in this part. By all the forces, work done by all the forces. If suppose you are taking a body and there is some work being done on that body. If there is some work being done on the body, in that case, if there is suppose change in potential energy also, that means there will be work done by gravity, which will be of course negative there. So if you consider the work done on a system plus the work done, that means this is the external agent which is doing work. There is work done by gravity also, which will be, suppose if it is being changed from one position to other, and it is your minus mgh or minus mgh2 minus h1. This is equals to change in kinetic energy. So there, if you consider this particular part, that is the change of the potential energy, you transfer it to the other side because it was having negative sign. So then you will have the kinetic energy plus potential energy. But that potential energy, where you are from getting that one, it is basically, that is also in the form of the work done by some force. So that is why when we say net work done by all the forces, not only just the external one which is applying the force, by all the forces, that one will be equal to change in kinetic energy. If friction is there, there will be work done by friction also. So there, if you take the change in kinetic energy, it is always there. Whatever is the work done against friction, if you transfer it to the other side, definitely you'll find the value of that kinetic energy will be less because there have been some work done against friction also. So this is for the statement of the work energy theorem.